Hi everybody, we are back and we are going to go through our P-Set4 solution videos. So, fill out all the sections. This is indium plus this. This is going to be liquid plus indium. This is going to be indium plus liquid. This is going to be liquid plus this. This plus this. This region is going to be this plus this. This region is going to be this plus this. This region is going to be this plus this. This region here is going to be this plus this. This region here is going to be this plus this. This region here is going to be this plus this. This region here is going to be this plus this. And then liquid plus this. Liquid plus this. This is going to be liquid plus this as well. This will be liquid plus this. This will be liquid plus this guy. This will be liquid plus this guy. This will also be liquid plus this guy. And the same thing here, liquid plus this guy. And then finally, beta plus liquid. And then alpha will be here. And then it'll be alpha plus this. And then also alpha plus liquid here. So there we go. Ugh, exhausting. But we got it done. Obviously, we want you to number it, but I'm going to be a little bit lazy. Congruent melting points. Here, here, where else? Here at 556, and then here. So that's it. Those are all the congruent melting points. Let's go ahead and label. So for example, I'm going to do eutectic, circle, oid, square. Oops, that's a square. Let me erase. I'm going to keep this consistent. Square. Peritectic. I'm going to do triangle. Oid. I'm going to do a star. So let's do eutectic first. There's a eutectic here. There's also eutectic right here. There's also eutectic right here. Let's do peritectic. Here's a 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 peritectic. Where else? Do we have any others? That's it. Any oids? Eutectoids? Peritectoids? I don't see any. And that's all there is. Great. 80% strontium at what? 800 C. So let's go ahead. We'll erase just this, but let's keep our legend. 80% strontium, 800 C. So we're going to go right about right here. So, what are the phases that exist? Only liquid. What's the composition and fraction? Composition is going to be equal 80% in the liquid phase. The fraction of liquid will be 100%, or 1, so 1.0. Chemical potential is just the chemical potential of liquid. That's the only, it's our lowest, we're in a single phase region. What are the degrees of freedom? So remember, degrees of freedom plus phases equals components plus 1. So our components are 2 components. Those are indium and strontium. Phases, 1, and it's a liquid phase. So what are degrees of freedom? 2. And we already did this. What are the components? Name them explicitly. Draw free energy curves at 770 C. So 770 will be just above this one. So let's go ahead. Let's draw it like this. Oops. But you kind of get the picture. Let me undo that. So 770, let's just draw it like this. Excellent. So I'm going to erase this. So what do we have here? How can we draw the free energy curve? So I'm going to change, actually I'm going to go change this color to, let's do black. Let's go here, here. So I need a dash line where I intersect one curve here, the curve here, and then the curve here, and that's it. So I'm going to draw, what are my phases? So here I'm a liquid phase. Here I'm a pure liquid phase. In between here and here, I'm a liquid, and I'm going to do this notation plus S1. S1 is going to be equal to INS In2SR. So then this next region is going to be also, so that's solid 1. This will be solid 1 plus, I'm going to call this solid 2. That solid 2 will be over, let's see, it's going to be this guy, so it's going to be In3SR2, and then that's going to be S2 plus liquid. So, oops, what's happening here? I like that. Well, I do really like that color. It's not my color here. So, in between, I need to have these common tangent points. So I'm going to go black to black. So I have a common tangent in this region, a common tangent in this region, and a common tangent in this region here. So when I draw my curves, I need to have this be the lowest. It touches here, this common tangent. So my curve has the same slope here. And then it kind of retouches here and then kind of staying low. You'll see in just a second. My solid phase has to be above here, and then it has to touch here. So it touches here, has the same slope here, and then it disappears. The green needs to come through here, touch at this point, have the same slope here, and then leave. And there we go. We got our free energy curves. So that's one problem down. Let's go ahead. Explain the concept of a common tangent. Our common tangent is equal to dg approximately dxb. So when we say like in two phases, my common tangent or my chemical equilibrium in liquid phase must be equal to the chemical equilibrium in the solid phase, we're saying that the slopes must be equal. This curve here is our free energy curve as a function of composition. So when we look at this two-phase region, a common tangent means the slope here and the slope here is equal, which is equal to saying chemical potential of liquid equals chemical potential of solid 1 because they're in a two-phase region. Different ways to say the same thing. All right, so let's fill out this phase diagram. This plus this for this phase, this plus this, for this phase, this plus this, for this phase it's going to be this guy plus this, liquid plus this again. For this phase, it's going to be liquid plus this guy over here. Here, this phase plus this phase, liquid plus this phase, liquid again plus this phase. Here, it's going to be this phase plus beta. This is going to be beta plus liquid in here. This is a tiny two-phase, because this is going to be beta plus liquid. This is pure beta. That will be beta plus this. This will be alpha plus this guy. And then this little two-phase region is going to be beta plus alpha in here. That's a tricky one. But that's our phases. Where's our congruent melting points? Here. Right here at 414. I'm going to probably do it with like a little dot. Here's another congruent melting point, and here's our final congruent melting point. So there we go. And then finally, eutectics, circle here, here. I believe that those are all the eutectics, which is fantastic. What else? What was our symbol for peritectic? Peritectic was a triangle. So if I see a triangle here. Fantastic. What else do we got? Ooh, what is this position right here? So I'm going from beta to a two-phase solid region. That is a eutectoid. I believe that would be a square. So that is a eutectoid right here. So let me erase. Right here is a eutectoid. There we go. We got it. Boom, boom. 20% thallium at 350. 20% at 350. So we're like right over here. So excellent. So we are in a two-phase region. So we are in Mg and also Mg5 TL2. I'm going to call this solid 1, solid 2. My composition of solid 1 will just be equal to, again, I'm going to run over here and I'm going to go down. So let's say that that's like 12. Composition of solid 2 will be over here, run here. That's going to be 29. So my fraction that's in the solid 1 phase will be equal to 29 minus 12, and I run away. So if I want to do solid 1, I want to go from 29 minus 20. And if I want my fraction that's in solid 2, it's going to be that same denominator of, but now it's going to be run away from there, so it's going to be 20 minus 12. And there we go. And it looks pretty 50-50, and that's what the variables say. Composition, so we've got 2 phases. Composition, chemical potentials, we know that they must be equal in each phase. What are the components? Components are Mg and TL. And then at 325, so 325, so let's just say we're like, 350, we're a little high here. So let's say 325 are about right here. So let's go ahead and draw those curves once more. Let's see if we can, yeah, I'm gonna delete some things. Good. So let's see if we can try to do the same thing we did previously. I'm going to draw it over here and here. This is free energy XB. Again, so we're going to go through right here. Then we're going to go through a 2-phaser right here. And then another one right here. And then another one right here. And then another one right here. And then nothing. So again, I am pure liquid here. Pure liquid here. I'm going to call, let's start to label actually the following. So I'm going to call, actually not liquid, ooh, excuse me, bad. So I'm going to call this, Mg is going to be S1. I'm going to call this S2. I'm going to call purple, I'm going to call this, oops, I'm going to call this S3. And then finally, at least I think finally, no, not finally, I'm going to call, let's see here. Let's do one. I'm going to call this S4. And then we got liquid here. So this will be liquid. So when I'm going through here, this will be, let's erase this. So I've got liquid here. I've got my S1 here. Then this is going to be S1 plus my S2. S2, this will be S2 plus my S3. And then I got, this will be, excuse me, S3 plus my S4, which is my orange. And this will be S4 plus my liquid. And then I'm going to draw my common tangents. Basically here, 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 and here, just kind of going down in a kind of a straight line. So my red solid 1 appears. It hits my 2-phase region, and then I'm gone. Then number 2, higher here, common tangent here, common tangent there, and then gone. My S3, hit it here, touches here, it touches the next region, and then it's gone. And then finally, actually not finally, here I'm going to touch right here, next region, and then gone. And then liquid finally here, touches over here, and then gone. And there it is. That is our last value. Problem set 4 solved. We'll see you in problem set 5. Thanks. Bye.